introduction, and hello everyone. So obviously this will be a talk about compilers and, well, not anymore. Well, that's a bug, but yeah, what was I saying? Yes, so this will be a talk about compilers. So as I guess you all know, that compilers are very powerful tools, but sometimes, I mean, we want to help them because they cannot do everything. And sometimes trying to help a compiler can backfire. And this work was in this work we studied this counterintuitive phenomenon. So a compiler is a very complex piece of software. It contains hundreds of moving parts that interact with each other while it optimizes programs. And sometimes even, or either through an improved analysis or through user input, a compiler can gain access to more information about the program that is being compiled, and it can use this to better optimize it. So for example, here we have a very simple program that just compares two integers and a simple function that compares two integers and a function bar that calls it, and we can also see our compiler's output. So as the programmer, maybe you have some additional context information that the compiler has missed. For example, maybe we know that whenever we call bar, x is at least as big as y. And we can encode it by using such an attribute. And essentially, this instructs the compiler that, hey, you can assume this while you're analyzing and optimizing this program. And if we look at the output, we can clearly see that it's slightly shorter. The compiler has figured out how to that it doesn't need to check everything that it did in the original program. But then the question is, do compilers always behave this way? Or can it happen that even though our compiler can already optimize the program, we somehow give it some additional information, and not only it cannot use it, but it ends up generating a worse binary. So let's look at a different example. Here we have a slightly more complex piece of code. We have some nested control flow, some for loops and if statements and so on. But as we can see, our compiler has figured out how to simplify everything. There's no control flow in the generated binary, just 5 assembly instructions. And the reason that it can do this is because the outer if condition of the if statement is always false, because the values of these are between -6 and 6, and our compiler can figure this out, and it generates this code. So now let's try to do something similar to what we did before. Let's try to add some information in our program. And what we will do is we will use the fact that the argument to the function called h is always non-zero. And we can encode it as an attribute on the parameter of the callee, so h. So we tell to the compiler that it should assume that j is always non-zero. Now what happens is that our compiler generates way more code, so more than 60 instructions instead of 5. And if we actually look at the resulting control flow graph, we can clearly see that something has gone off the rails. Now we get all of this complexity, whereas in the beginning we just got these 5 assembly instructions. So what went wrong? The attribute that we added is encoded in a construct that more or less looks like this. So what this says is that if this expression that corresponds to the argument is equal to 0, we are in an unreachable state. And so the compiler can assume that we will never reach that state. And all is well up until now. It can still figure out that the if statement, its condition is false, and it can delete everything. But there was a recent change that landed in GCC 14 that simplified this expression to something like that. So it got rid of the arithmetic that was in that expression. And somehow, the value range propagation pass that was responsible for propagating all the information to that if statement can no longer figure out what is going on. So it can no longer eliminate the dead code, and cannot simplify anything, and then we end up with this complexity. So on one hand, we have this slight simplification, and nobody would argue that it's something that a compiler shouldn't do. If it can simplify an arithmetic expression, why not? On the other hand, this ended up revealing something that was missing, that was not properly implemented in this value range pass, and the compiler can no longer figure out what's going on. So we have this unexpected interaction between two of the compiler's components, two of its passes, that end up causing this situation. So the goal in our work was to study this phenomenon, to understand, first of all, how frequently this happens. But we also wanted to find such cases and report them, not only to study them, but also to report them to compiler developers in case they want to also fix them. So how do we find these cases? How can we find examples such as the one that I just showed? So we do this via automated testing. And we essentially use a randomized program generator, so CSmith in our case, to generate candidate programs. And what we want to do with these programs is essentially what I just showed. So we want to somehow modify them and then check if the compiler is misbehaving or not. And the first thing that we need to do is we need to figure out what kind of information will we inject in that program. And in order to figure this out, we simply run them and observe their behavior. So for example, we track maybe what are the values of the particular variables, what are the lower and upper bounds. And now that we have this information, we can modify the original program and create a refined candidate, one whose static behavior is a bit more constrained based on this dynamic information that we have observed. And now that we have our two versions of the same program, we can simply compile them. And then now we need to decide, did the compiler do something that it couldn't do, or sorry, did the compiler not do something that it could before? So essentially, did it miss some kind of optimization? And if it has, then we have found an interesting candidate. If not, we can just keep iterating until we find one. So I'll now briefly explain how we implemented the various steps, except for the first one, because that was an off-the-shelf program generator. So how do we derive information? How do we figure out what we want to eject? In this work, we focused on two kinds. One is dead branches. So we want to know which if statements are never executed, or which for loops and so on are never executed in the program, or the test program. And the other one is value ranges. So what is the lower and the upper bound of particular variables at various program locations? And the way we track this is by source-to-source transformations. So for every branch, we inject some tracking code that at runtime will record, was this branch ever run or not? We do similar stuff for the various kinds of loops. And for variables and their value ranges, we also do something similar. At runtime, the code just observes what are the various values that this variable assumes at this particular program location, and then it tracks its lower and its upper bounds. So now that we have this information, we want to modify our program. We want to constrain statically its behavior based on this runtime information. And the way we do this is via compiler built-ins. So you already saw one example with assume attribute, but here for the dead branches, we use something different. We use the built-in unreachable, which essentially instructs the compiler that the program will or should never reach that location. And this enables the compiler to do two things. First of all, it can prune everything that follows in this particular block. And what it can also assume is that the condition will always be false. And it can use this information throughout the program analysis and optimization. And for the value ranges, we also use a call to this pseudo function built-in unreachable, but this time we guard it with the opposite condition of the one that we know is true. So here we have recorded, or we have observed, that a variable v will always be bounded by a lower and an upper bound. So we are in an unreachable state if this condition doesn't hold. And similarly to before, the compiler can use this information potentially while optimizing this program. So one note is that both of these things would have been probably much easier to implement as compiler passes and not source-to-source transformations. But since we were targeting multiple compilers, we wanted a single solution, and that's why we opted for a source-based one. So now that we have our modified program, we need to decide, did the compiler misbehave? Did it do something that, or did it miss some optimization that it didn't do before? And for that, we need what we call an oracle that will essentially take the two binaries and somehow compare them. And in this work, we tested three different ones. The simplest of the three is essentially binary size. Say that somehow I add somewhere in one built-in unreachable, and suddenly my binary becomes much larger than before. So this is a sign that something has gone most likely off. And one note is that this only makes sense if we're optimizing for program size. If I say, for example, if I optimize with or compile with O3 where things like loop unrolling or vectorization might happen, such an oracle doesn't make sense. So this is kind of a special case. But a different oracle that is slightly more fine-grained is the one based on dead code elimination. So say that there's a piece of dead code in our original program that our compiler can remove. So it doesn't, code for this is not generated in the final binary. But somehow now we added some of this information in the refined program, and our compiler can no longer eliminate this piece of dead code. This is a sign that something has gone off during the optimization or the analysis of this program. And the third oracle that we used is one that targets the value range capabilities, of value range analysis capabilities of the compilers. So what we want to test here is, can the compiler figure out that a particular variable will always be at a particular program location between a lower and an upper bound in the original program, but not in the refined one? So doing this in a compiler agnostic way is a bit tricky, but what we did was to reduce this problem to, again, a dead code elimination identification one. So say, for example, that we have a variable that is, we know that it's always positive. What we can do is, in the original program, we can inject a piece of dead code that is guarded by the opposite condition. And now, given that we know that V will always be positive, we also know that this piece of the code inside the if statement is dead. And the interesting case is if the compiler can remove this in the original program, but not in the refined. So again, this kind of estimates that the code that we added probably interfered, and the compiler can no longer figure out that in the refined binary, V was probably always positive, whereas in the original it couldn't. And there are some caveats here. If you have to inject this in a live part of the program, not in a dead one, because then you're really not measuring anything. But these are implementation details. The basic idea is this. So this is our end-to-end testing pipeline. So, and it's also available together with instructions in the link shown on the slides. So we use this pipeline to identify and also report a number of such cases, such as the one that I showed, both on, for GCC and LLVM, around 16 total, most of which have been either confirmed or fixed. And a lot of these are either, for example, some of these are related to buggy implementations where some analysis or some transformation wasn't properly implemented. Others are about missed cases that were not implemented in that particular compiler pass. Or some of them are related to unexpected interactions where the compiler developers implemented something and they couldn't foresee that downstream this might hurt another compiler pass. So one thing you might be wondering is, okay, we can find all of these cases, but how diverse are the root causes? Could it be that there's just a small subset of the compiler that is causing all of this, or do we have a diverse set of issues? And one way that we tried to answer this question is the following. We analyzed a number of regressions, and for each regression we know what was modified in the compiler. So we know that, for example, maybe there was a change in some alias analysis pass, and after that change we can detect this kind of behavior. So we analyzed a bunch of them, and then we counted how often do the various compiler transformations or analysis, like value range propagation, peephole optimizations, and so on, trigger these unexpected and counterintuitive behaviors. And it turns out that we can find them pretty much everywhere. And it's not only these passes, but it's kind of these together with the interactions of or the interactions between them. So now that we have this functionality, we can try to answer the other question. How prevalent is this phenomenon? Does this happen very often or extremely rarely, and we shouldn't care about this? So we did the following experiment for this. We generated 10,000 programs with CSmith, and we used two compilers, GCC 13 and LLVM 16. And for each of these programs, we essentially run our pipeline. So we ran the program, we observed its information about it, injected it, and then used the one oracle to figure out, do we observe this weird behavior? And we used the DC oracle. So essentially, we just tested if there was some piece of dead code eliminated in the unmodified program, but not eliminated in the modified one. And it turns out that in around 9% of the test programs, we could trigger this behavior in GCC, and around, 17%, and 9% we could trigger with 9% of the programs, we could trigger this with LLVM. So this shows that at least in auto-generated code, this is not rare at all, and we can very reliably trigger this behavior. But now you might be wondering, what about real code? Does this happen on code that actual users write or not? And if you browse through the bug trackers of both GCC and LLVM, or the discourse of LLVM and the mailing list of GCC, you can actually find a lot of reports by users that are complaining, or maybe not complaining, but reporting similar issues where they try to help the compiler either via built-ins or intrinsics or modifying their source code, and they ended up with a worse result than what they had originally. So to sum up my talk, in this work we focused on this unusual behavior of compilers where sometimes we try to add some information to our programs and this ends up confusing the compilers and they generate way worse code than they did without it. And for this we developed an automated testing based approach that can find such cases, and we used it to both identify a number of them and report them both to GCC and LLVM. And we conducted a systematic study, and there are more details about it in the paper. And maybe the one takeaway of this work is that compilers can sometimes behave very unintuitively, especially from the perspective of the users. And a challenge for our community is how do we actually build compilers that always behave intuitively and predictably? And what kind of tools and research do we need to do in order to achieve such a goal, especially for these interactions with users that are trying to fight or help the compiler. So thank you for your attention, and I'm ready for questions.
Questions? There's a mic here in the front. All right. Rush. Yes.
Hi, Peter Roman, St. Ben, St. John's. Very interesting. Thank you. I appreciate the work. I think I have one question. It might be two, but I think it's one. So my question is about how you analyze the results, how you did your Oracle, especially for dead code elimination. But I'm specifically interested in just like how different the programs tended to be when you added in the hints, right? So I guess the big, how did you know whether dead code was eliminated? Because I'm guessing the programs were not always identical except that some code was gone. I'm guessing they were often more different than that. Does that make sense?
Yeah.
Okay. Great.
So we have a previous work that would, a paper that would exactly answer your question, but I'll give a brief description. So essentially what we need to do is we need to add something in that program, in the original program, that we can very easily detect in the binary. And if we can see it in one binary and not in the other, we kind of know that something has been eliminated in one and not in the other. And what was the second question? How different okay, so after we add this information, how different the program looks like. So there's so we have a lot of freedom there, because what we can do is we can simply add one built-in unreachable call in one place, or we can litter the program with pretty much a ton of them, right? So we were actually doing this for every such case that we detect, that we only add one hint, which makes the testing a bit slow because you have to test a lot of stuff, but it's probably more reasonable than adding just thousands in every test program.
Yep. Thanks for the talk. I was wondering, kind of the point of these annotations is that the code becomes faster, but you're showing it actually doesn't become faster. And like this 9 or 70% number is quite high, where you actually don't get faster code. I was wondering whether you found certain guidelines or ways how you can actually use the annotations that you know it will actually work, or some. Yeah.
So there is a post in the LLVM discourse called something like built-in assume, which is kind of similar to this one, is highly misused. And the problem is that what you need to know is you need to know what the compiler needs and what it couldn't figure out. Because if you blindly start adding stuff, you can, as we showed, you can clearly confuse it. So ideally, we would have a compiler that asks the question, not the other way around. But unfortunately, compilers don't do that. So I think the best answer is you have to see what the compiler didn't do that you wanted it to do, and then figure out what you need to include or how you need to modify your program. But
I see. And then you need to manually check that you actually didn't confuse.
Yes,
the compiler
exactly.
byte. Okay, yeah, thanks.
Great. Let's thank the speaker for once more for answering the questions.
Thank you.
Then the next talk